We're live. The Atwood machine is a pulley system, as seen below. You know what? Look up. Here's an Atwood machine. What we mean, Owen, by an Atwood machine is when one mast goes down, the other mast goes up, and they're attached by a rope. Except we're in our magic physics world. To make the math nice, our ropes have no mass, because that would change the equation. And our pulley has no mass or friction, because that would change the equation. So let's pretend that this pulley is really, really, really greased down. The only masses in the equations are the masses on the ends of the ropes, not the ropes themselves. Typically, one mass is called the mass, the other mass is called a counterweight. This is often how we have elevators set up, for example. There's a counterweight that you don't know about. And so here's our first thought problem. Suppose equal masses are placed on both sides of the Atwood machine, like this, and one of the masses is allowed to move up. If I let go of the higher mass, this one, and there is no friction, if this is a perfectly massless, frictionless pulley, what will happen? Option number A, nothing. The system will remain at rest. Option B, the higher mass will fall down because of gravity. Or option C, the higher mass will go up because this one's closer to the Earth. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So you got the thought problem? We have an Atwood machine. We raise one mass up. We lift up that mass, and then we let it go. What's going to happen? A, nothing. B, the higher mass is going to fall because stuff falls when you lift it up. Or C, the higher mass is going to go higher. Who says A, Mr. Dueck? Nothing's going to happen. A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Who says, Dueck, it's easy. The higher mass is going to fall. B. 1, 2. Who says, no, the higher mass is going to go higher when you let it go? Okay. I'm not going to answer it. You know what this is a good job for? You know what this is a good job for? I'm going to do a free body diagram, and I'm going to do a free body diagram on this picture here. Let's look at this left-hand mass. What are the forces acting on it? Get the obvious one. So I'm going to call it M1G. And I guess there's tension. Yes? What are the masses? What are the forces acting on the right-hand mass? Get the obvious one. And you know what? Since they're the same mass, normally I would call one M1 and one M2. But since they're the same mass, the question says, I'll call that M1G and tension. Now, some people said nothing happens. Some people said the higher mass falls. Let's pretend option B is correct. If the higher mass was falling, you're saying that things are going to accelerate that way. So we're going to do our equation, winner minus loser. We're going to do all of the forces along the rope. Anything that ends up pointing down once it gets to the left-hand side is going to be winner plus. Anything that ends up pointing up once it gets to the left-hand side is going to be loser minus. If I write an equation then, I think I would have this. M1G, that's that one. And then I would have minus tension. Now, this tension right here, you might think because it's pointing up, it's a loser. But if you follow it all the way to this side, I think when it gets to that side, it ends up pointing down. And so that tension, Amy, is going to be a winner plus. This M1G on the bottom right here, you might think since it's pointing down, it's a winner plus. But again, Harry, if you follow it, when it gets to this side, I think it's pointing up. So I'm going to call it a loser minus. Oop. And that's going to equal M all A. Why am I stretching out? I lose tension. Why am I scared? Why do I have tension back again? What else cancels? What? Well, when everything cancels, what number is left behind? So I have this. 0 equals m all a. Well, this is saying 0 equals something times something. Is the mass 0? No. So what must be 0? Gotta be. Therefore, acceleration has to be 0. So what's the correct answer? A or B or C? What must the correct answer be?
A.
And there's two possibilities, by the way. A could be correct, or if I started it going at a constant speed and just let go, it would just keep moving at a constant speed until we ran out of rope. A. Where it says explain your answer, that there, I would say, would be a lovely proof. Almost, in fact, no English, no words, no numbers, nice and algebraic. If I saw something like that, if I gave this to you as a using principles of physics question on a test, my little math nerd heart would just go pitter-pat. I'd say, oh, that's nice. Okay? Yeah. Quick look at money. Example 2. Yeah. With a pulley again? Yeah. The problem here is there's a lot of friction. But for what it's worth, if I do this, doesn't start to accelerate. And even if there was no friction here, it wouldn't start to accelerate. What's smart, the elevators are built like this so that you don't see this. Somewhere in the elevator system, there's a counterweight that's the same mass as an empty car. So that when we lift the elevator to the 4th floor and everyone gets off, the machinery can shut down. We're not having to waste any energy holding the elevator car on the 4th floor. We're only using energy to move the car up and down, but we're not spending, because most elevator cars are at rest for most of the time, we're not using any energy or wasting any energy, just holding it in place. So it actually is a quite clever system, the Atwood machine. You okay with that? I like example 2. Well, you know what? Actually, that's a lie. Example 2 is physics 11. It's a little bit too easy, but I might throw it at you on a quiz or a test as a hopefully get some free marks, but I'll show you what I would consider to be physics 12 with an Atwood machine. It says, find the acceleration, find the tension, assume m2 equals 5.8. Assume m1 equals 2.3. And notice M1 is not sitting on the surface, so no normal force. If it was, I would just add a normal force in my diagram. Okay. How am I going to start this? Darn right. But did they give me a picture? Then I'm going to label the picture and be lazy. What are the forces on the left-hand mass? Get the obvious one.
Mg and
I'm going to call it M1G since there's more than one mass. Tension. And on the right, M2G. Tension. Cole, coming back to you, who's winning? Are the masses equal this time? Who's winning? The bigger mass. But which force is winning? Don't say M2. Which force is winning? M2. And so what you've just decided, Cole, is that anything that ends up pointing down once it gets to the right-hand side is going to be a winner plus. Anything that ends up pointing up is going to be a loser minus. So you ready? Walk along the rope with me, Cole. Who's winning? Who's the loser? Oh! You didn't see Ryan. I said, who's the loser? And he looked at you. Oh. You should not be friends anymore. In my free body diagram, who's the loser? Tension. And then I have another tension, which in this case ends up being a winner plus if you follow it all the way around to the other side. And then minus M1G ends up being a loser minus when you follow it. Do I have forces from more than one mass on the left-hand side? Then I better have forces from more than one mass on the right. Well, I better have more than one mass. It's going to be M all A. Oh, lose a little tension. Cole, how would I get the A by itself? In fact, I'm kind of lazy. I'll often just do it like that, and now I can go straight to numbers. M2, 5.8, G, 9.8, minus 2.3 times 9.8, all over 2.3 plus 5.8, which is what? Again, make sure you're comfortable typing these into your calculator. For me, I have to put brackets around the top. You get 4.234, that 4.23? Or am I off? Yeah? 4.23, 4, 5, 6, 7, 9. Oh, that's an interesting pattern. 2, 3, 4, 5, 6, 7, 9, 0, 1. Don't know if that's a repeating decimal. It probably is. Yeah.
I got 8.21.
Pause for a second. Don't clear your calculator. 4.23. I'll store this on my calculator. Cole, what else do they want me to find? What's B want me to, oh, sorry, that's part A. Tension. Chelsea, how am I going to find tension? I'm going to look at one mass. Which mass? Honestly, it doesn't matter. Typically, you give me a choice, I'll pick the mass where tension is the winner because it's slightly easier to get the T by itself. So I would choose this one, but I don't care for what it's worth. So I'm going to go tension minus M1G equals M1A, or you could go M2G minus tension equals M2A. You're going to get the same answer no matter what. So tension, see, and the reason I kind of like this one, Chelsea, look up, I would be lazy enough to now go and just do that on the same line without rewriting it, but I've still been organized and I've still showed my work, and then I can go tension equals 2.3. I'm going to write 4.23, but I'm going to use my answer button right there, plus 2.3 times 9.8. 2.3 times answer button, plus 2.3 times 9.8. And I get 32.3. The Atwood machine. Example 3. Okay. Consider the following system. Which of the following is the best free body diagram for mass 2? Is there friction in this question? No. It says mu is 0. Okay. What mass is force F pushing on? Is it pushing on M2? Okay. Let's see. You know what? Let's go systematically. I'm actually going to do the forces acting on mass 1 first. Now, I know there is this one here, but I'm going to have M1G normal force number 1. Which way is mass 1 going to accelerate? Right. And when it starts to accelerate right, what does it run into? Mass 2 is going to apply a force that way. This force, though, look up, it's on mass 1, so I'm going to put it from the middle going this way, and I'm going to call this F contact, a contact force. That says contact. You can barely see it because I wrote it really, really small. So I'm going to call it FCON for contact. Okay? So mass 1 has 4 forces acting on it. What are the forces acting on mass 2? Get the obvious one.
M2G.
What else? Normal force 2. Which way is mass 2 going to accelerate? Okay, so there has to be a force, an unbalanced force, pointing right. Which force is that? Normal force is pointing straight up. Which force is making mass 2? Because forces come in. So Ryan, I heard you blurt out C. What is the correct free body diagram here? Okay? But here's what I want you to realize. If we don't panic, everything that I've taught you in Physics 11, we can even handle weird new stuff as long as you meticulously really fall back on Newton's laws. You notice I kept saying, which way is it going to accelerate? That tells me at least where there's got to be an arrow pointing, an unbalanced arrow pointing. But I also said, look, looking at mass 1, because that was less scary than mass 2, I know mass 1 wants to accelerate right, but it's going to run into something. And so I've invented this thing. I'll call it a contact force. You could also, by the way, have called that a sideways normal force. That's often what I'll do if I'm pressing against a wall. I'll call it a normal force, and I would be fine with that. But we had to do something. Okay? Explain your answer. I think we did in our good free body diagram. I'm not going to write out a big paragraph. So let's do one with numbers. It says, find the acceleration of the system and find the contact force. Okay. We're going to have F applied. Definitely M1G normal force number 1. And then we said we know mass 1 is going to want to accelerate to the right, but it's going to run into mass 2. So mass 2 is going to apply a force to mass 1, and we call that the contact force. Ooh, we're also pushing on it from the left. Okay, so there's going to be F applied number 1, and how about F applied number 2? To go with mass number 2. Gravity down. Normal force up. Oh, and there's going to be a contact force to the right. What's the real tug of war here between which two forces? Can you see it? The F applieds. Who's winning? Which direction is going to be the winner direction? And this time, I'm going to start on this side and walk to the, because that's the main winner, and I'll follow it that way. Usually I start on the right and work my way to the left, but I can adapt. So my equation is going to be winner minus loser plus winner minus loser equals what? M all A, because I have forces from more than one mass on the left-hand side, so I better have more than one mass. The contact forces cancel, and in fact, I guess A is going to be F applied 42.5 minus 6.75, all divided by 6 plus 8.25. Matt, is this a fraction? Brackets around the top. Is there more than one thing on the bottom? Brackets around the bottom. And I get, first of all, I got a positive answer, which is reassuring, because if I got a negative answer, I would have gone, boy, have I misunderstood this question, because I'm pretty sure it's accelerating in the direction that I picked. I'm going to write 2.51, but I'll store this on my calculator. Is it 2.50877.193? So I'll go 2.51 meters per second squared. That's only the first part. The second part, they want me to find the contact force. Both of these are equally yucky. I'm going to use mass 2. Why am I going to use mass 2 to find the contact force? Because I think the contact force is pointing in the winning direction. That's the only reason. Oh, also, if I added friction in this question, can you see you just have two more losers, one from each mass? I can't really make it tougher. I can only make it longer. What was that? No, they would not. They'd both be pointing in that to the left, right? So I would have to include them. Anyhow, I'm going to say, okay, contact minus 6.75 equals m2a. I think that's the horizontal equation for the second mass. So I think the contact force is going to be m2a plus 6.75. I'm going to go straight to plugging in numbers on my calculator. M2 is 8.25 times answer button plus 6.75. And so now I've introduced to you this weird thing called a contact force, but I hope I didn't actually teach you anything new. I just helped you make a good educated guess and say, oh yeah, that ties in with what I know about Newton's laws. Of course, I might have called it something different. Ben, you might have called it a horizontal normal or normal x. Fine. 27.4. Okay. Example 5. A curling rock is traveling east across a sheet of ice. It bumps another rock and experiences a force that acts very briefly to the north, so only during the collision. What will the path of the rock be after the bump? A, B, C, or D? So the rock is coming in. It receives a brief bump in the vertical direction, in the north direction, however you want to think of your paper. And then the rock 1 continues on. What will its path be after the collision? A, B, C, or D? And convince me. Yeah. Why must it be D? Well, don't say F resultant. First of all, after the collision, not during, after the collision, are there any forces acting on it? So Newton's first kicks in. It's going to go in a straight line at a steady. So it can't be that one. That would imply that there was still a strange force acting on it. But was there a force applied to it during the collision? So it's got to change its direction. It's got to accelerate. Yeah, it's D. Okay. We're going to do example 7 first and come back to example 6. Example 7 is physics 12. I like example 7. I like example 7. I like example 7. Example 7 is a nice question. Example 7 is an Atwood machine. But what am I asking you to find, Adam, in example 7? I'm reversing the question. I gave you Atwood machines in grade 11. I gave you both masses. I said find the acceleration, find the tension. Here, I'm either going to give you the tension or the acceleration and say reverse engineer it to find the missing mass. Having said all that, you know what this is a good job for? Free body diagram. What are the forces acting on M1? Get the obvious one.
M1G.
What else?
Tension.
And M2G, tension. If I don't give you both masses, I have to tell you which way we're accelerating. Otherwise, it's impossible to solve. Oh, which one is accelerating? Sorry? Which one is accelerating downwards? What does the question say? So A is in that direction. I'm going to say the same thing. I'm just going to phrase it differently. The winning direction is in that direction. Why can't I go my usual winner minus loser equals M all times A? Because in that equation, I would have multiple unknowns. Instead, since you didn't give me both masses, I'm not going to write an equation for both masses. I'm going to go look at one mass, the mass that I know. Adam, which mass do I know? Looking only at M1, which way is, sorry, M2? Which way is M2 accelerating? Who's winning? Who's losing? Equals M2A. What can I find from this? Tension. Or I'll give you tension, and what can you find from this? Acceleration. Swappy dance? Now, I think I did an example like this in Physics 11, but I told you I wasn't going to test you on this in Physics 11. Physics 12, absolutely. Missing masses. Tension is going to be M2G minus M2A. Put your calculator down, Adam. How many masses do I have? Oh, no, I'm good. Never mind. Put your calculator. Pick your calculator up. I apologize. I was getting ahead of myself. Meathead, Mr. Dueck, pay attention. What was it? 8.4 times 9.8 minus 8.4 times 3.5, and I get a tension of 52.92. We're going to repeat the same procedure for mass 1. Oh, and what are the forces? Oh, which way is mass 1 accelerating? Who's winning? In mass 1, I'm going to have tension minus M1G equals M1A. And I'm trying to find M1. How many M1s do I have? 2. Ben, how many would I prefer? Let's get them to the same side. How many M2s do I have? Sorry, how many M1s do I have? How many would I prefer? Factor. It would be wonderful if there was a Math 9 operation that would help me change this from 2 M's to 1 M, and there is. So I guess M1 is going to be tension over A plus G. Well, that's easy, Mr. Dueck. I'll just memorize that. No, the equation varies depending on whether M1 is a winner or whether it's a loser, or if I throw other stuff in there. So please don't memorize, learn to derive. But it is going to be 52.92. If this hadn't worked out nice, I would use my answer button. And what was A? I've scrolled down. 3.5 plus 9.8. And I get mass 1 has to be 3.98 kilograms. You're now capable of doing any question from the ultimate review that doesn't have an incline or a ramp or something slanty in it. Okay. Oh, not pause yet. Go back to this question, please. Example 6. Suppose we take a water bottle and we drill it with many small holes so that it leaks when it's filled up. If the bottle is filled up, but then it's dropped while it's in the air, what happens as it falls? A, the water stops leaking out. B, the water leaks out at the same rate as before. C, the water leaks out at a slower rate. Or D, the water leaks out faster. We're not going to vote. Instead, I'd like you to jot down what you think the correct answer is, A, B, or C, somewhere in that area. And then we're going to go do the experiment. Homework. You can try... Well, okay. Let's go the first number 2. You can skip the M with the algebraic one, so 2, the first one. 3 is good. Yeah. 8 is good. 9 is a nasty scholarship challenge. I'll give that to you. If you can get this, I'll be impressed. This is a challenge. Far tougher than I would ask on a test. But absolutely 10 is fair game, finding a missing mass. So not too many questions, although you also have a take-home quiz. And you can start to, if you want to, whittle away at the ultimate review.